Let us find out moment of inertia of some simple objects. First, we'll take the example of moment of inertia of a uniform thin hoop. Hoop means a band, a ring-like structure. This is a band or what you call a hoop. We want to find out the moment of inertia of this hoop, which is having a mass m. It is having a radius r. It is rotating about an axis which is passing through its center. So about this axis, the hoop is rotating. We want to find out the moment of inertia. We are going to consider a small strip of this hoop, a small section of this hoop we are considering. This is the radius r. The total length of this hoop is 2 pi r is the total length. If m is the total mass, the mass per unit length of this hoop will be m by 2 pi r. 2 pi r is the whole length. If you open it up as a strip, it will be of length 2 pi r. If total mass is m by 2 pi r is the mass per unit length. I am going to consider a small section of this hoop of length ds. ds is the small length, and it is the mass of this small piece of this hoop is mass per unit length lambda into ds, because ds is this small length of this hoop. Unit length, it has got a mass lambda, so lambda into ds will be the mass of this small strip over here. Now let us find out what is the moment of inertia of this small strip. Moment of inertia I equal to I is integral rho square dm. Our expression we have derived in the previous class. Rho is the distance from the axis. Here the distance from the axis is r, the radius of this hoop. So rho is equal to r. So instead of rho square you can substitute r square. Instead of dm you can substitute lambda ds. So our moment of inertia I will be equal to integral r square lambda ds, and the integration is from 0 to 2 pi r. 2 pi r is the length of this strip. So starting from 0, if you cover 2 pi r, the entire length of the thin hoop is covered. So when you integrate this, r square is a constant. Lambda you substitute m by 2 pi r. It is also a constant. You take it outside. Then you have integral ds. Integral ds is s, limits 0 and 2 pi r. You apply the limit, upper limit you apply r square m by 2 pi r into 2 pi r, that will be m r square, minus, when you substitute s is equal to 0, this will be 0. So moment of inertia I will be m r square, where m is the mass of this hoop and r is the radius of the hoop. Another example is a uniform disk. You are considering a uniform disk. This uniform disk is having a mass m. This is the area of this uniform disk. R is the radius of this uniform disk. Moment of inertia I, as we have derived previously, it is integral rho square dm, where the rho is the distance of the jth particle and dm is the mass of the mjth particle. We are going to divide this uniform disk into small hoops. We can consider this as made up of a hoop like this, another hoop like this. So concentric hoops, you can imagine this to be divided into. One such hoop, one such section I am drawing here, it is having a thickness d rho. D rho is the thickness of a small hoop you have considered over here. It is at a distance rho. Okay. So the area of this hoop will be 2 pi rho into d rho. 2 pi rho into d rho will be the area of this hoop. M is the total mass of the disk. We can find out mass per unit area. Mass per unit area is, the total mass is m, total area of the disk is a, m by a is the mass per unit area of this disk. So from that, the area of the hoop we have considered is 2 pi rho d rho. So mass of the small hoop dm can be written as mass per unit area into the small area. Substitute for area 2 pi rho d rho in this case, and moment of inertia of this small hoop we have considered di is rho square dm, that is rho square into, instead of dm you can write m by a, dA is 2 pi rho d rho, substitute for that. A is area of the disk, which is pi r square. So finally you get it as 2m rho cube d rho by r square. That is the moment of inertia of this small hoop you have considered inside this disk. Like this you have to find out the moment of inertia of all the hoops constituting this disk. For that you have to integrate di in the limit 0 to r. That means the radius changing from 0 to r, if you integrate for all the hoops, you will get the moment of inertia of the disk. So substituting I equal to integral 0 to r, instead of di I can substitute 2m rho cube by r square into d rho. M and r square are constant, you take it outside, you get it integral r, integral when you rho cube, when you integrate you get rho raised to 4 by 4 and the limit is 0 to r, substitute for that and you simplify, you get it half m r square. That is the moment of inertia of the uniform disk.